Hi, welcome back. In this lecture, I will introduce the finite element method, in short, FEM. In the FEM, the domain is subdivided into small subdomains of simple shape, for instance, triangles. As initial example, we might want to consider a circular domain in two dimensions that is subdivided in triangular subdomains. The collection of triangular subdomains cover the original circular domain, and the triangular subdomains do not overlap each other. Hence, the circular boundary is approximated by a polygon that consists of the outermost edges of the triangular subdomains. So you can see here the boundary consists of different segments that approximate the circle. So one of the most important concepts when we use FEM is to understand that we are going to use an approximation of our fields, electric field, magnetic field, or the potential. We are going to use an approximation that use a low order polynomial. So for instance, we can use linear polynomials on each of the subdomains. So for instance, we can consider subdomains that is going from x3 to x5 in this plot, and our approximation is just this piecewise linear function. So we're going to have this tend-like function that is going from 0 to 1 x4, and then x5 then is linear decreasing. As out this element, this function is 0. So this is just an example of a piecewise linear polynomial. In general, such a representation of the fields is not flexible enough to able to exactly fulfill the differential equations in a pointwise manner. So we use a second trick that instead of enforcing equality pointwise, we ask this equality to be true, to hold in the weak sense, so in a weighted average sense. So the finite element methods relax these requirements on pointwise equality when we attempt to find the field solution that fulfill the differential equation. We relax this condition and we find this equality in average sense that is called the weak form. So there are different approaches of how to construct this relaxed fulfillment, that is to have equality in average sense. There are two important methods to derive the FEM. The first one is to set the weighted average of a residual of our differential equation to 0. A second method is actually to exploit a variational method to find the stationary points of a quadratic form. So also this second method uses a variational principle to derive the methods. In this course, we focus on the first method. So the way that we are going to derive the FEM method is to use a set of weighted average of the residual to 0. For a FEM that works correctly, the approximate solution tends to the exact solution as the size of the subdomains tend to 0, and consequently the number of subdomains to infinity. So we know that reducing the size of our domain of our elements, the solution will converge to exact solution. So what are the advantages of the FEM? Well, a very strong point of the FEM is its ability to deal with complex geometries. The FEM method typically uses unstructured grids, which are commonly referred as unstructured meshes. These meshes may consist of triangles in 2 dimensions and tetrahedra in 3 dimensions. Unstructured meshes with, for instance, tetrahedra, allowed a good representation of curved objects, which are quite hard to represent on Cartesian grids used by finite difference methods. So in this slide, I show an example of an arbitrary object with quite complex boundary to represent. So this is the finite difference using Cartesian grid uniform, and we see that we have this staircase effect when we try to approximate the boundary of this object. However, when we use the finite element approach, the approximation of the boundary is much better. You see that we are using different triangles that might be of different size, so we are using unstructured meshes. And you see that the error when describing the boundary is much lower than the error that we have when using the finite difference approximation. So what are the disadvantages of FEM? Well, a disadvantage of the FEM compared to the FDTD is that explicit formula for updating the fields in the time domain simulation cannot be derived in a general case. However, we need to solve a linear system of equations in order to update the fields. As a consequence, provided that the same numbers of cells are used for the two methods, the FEM requires much more computer resources, both in terms of CPU times and memory. So why is that? Well, the reason is that compared to the FDTD, where we just update the values of the electric field and magnetic field, what we are doing here is to solve a linear system. So we see one step is to form a linear system, and the second step is actually to solve the linear system using, for instance, a linear solver like conjugate gradient, GMRS, or LU decomposition. So normally the FEM is used to solve a differential equation, and in this particular module we focus on using the FEM method to solve differential equations. However, it's also possible to apply the FEM to integral equation, where the unknown field is part of the integral. In SEM, the FEM applied to the integral equation is referred to as the method of moments, and this technique will be discussed in the next module of this course. So this is the last slides of this introduction to the finite element methods. In the next lecture, we're going to look at how to derive the finite element method, what is the simple recipes to arrive to a formulation of the FEM. Talk to you soon.